Hello everyone, today we're going to talk about Chapter 6, Integers and Divisibility. First of all, definition. All of you should know those two definitions by now. Those were tested kind of in your first quiz, so we'll skip this. The new thing is division algorithm. Although it sounds new, but it's something everyone seen as in elementary school. So if we have a and b in natural numbers, then there exists a unique pair of integers. Notice that this is unique, okay? Then there exists a unique pair of integers q and r, with q greater than or equal to 0 and r smaller than b. This is quite important, such that a equals to q times b plus r, and q, as all of you should know, its quotient, r is a remainder. I have some examples here. I'm pretty sure everyone knows how to do them. One thing I want to emphasize is, well, right here, r has to be smaller than b, okay? Yeah, I use different color here. This is your b, this is your r. Everyone should know this by now. Anyway, let's skip this part. Definition, greatest common divisor, GCD. I'm pretty sure a lot of you have already know this from high school, but it is the largest integer that divides both numbers. So if we have GCD a and b equals to 0, then they are relatively prime or co-prime. Co-prime. Proposition. If a, b, k are integers with a, b both not 0, then GCD a b equals to GCD a minus kb and b. Here they are talking about GC a and b are both not 0. This is because GCD, the minimum value of GCD is 1. It cannot be 0. Okay, so GCD 0, 0 is undefined, because the smallest number of GCD is 1, which is a natural number. So your GCD can only be natural number, not smaller than that. This proposition, I personally think it's quite important. So I wrote an example right here. Okay, example here. So we need to find GCD of 3n plus 2 and 2n plus 1, where n is some natural number, no, not natural, integer. So we can apply this proposition. So this equals to GCD 3n plus 2 minus the second number right here, and 2n plus 1. And 3n plus 2 minus 2n plus 1 equals to n plus 1. So we apply this proposition again. We have GCD of n plus 1 and 2n plus 1 minus n plus 1. So here and here, okay? Eventually we get GCD of n plus 1 and apparently the GCD will be 1. As you can see, it is quite useful. I would say not always useful, but sometimes it's quite useful. And it's much faster than using Euclidean algorithm, the algorithm we're going to talk about right now. I copied paste the whole procedure here from your textbook, but personally I don't like to read, so I learn best by doing questions or checking examples. So I gave you an example right here. This is from the tutorial activity of week 13. I'm pretty sure TA did this in your tutorial, and I'm gonna go over the same thing again, because this chapter is kind of like computation. As long as you know how to do one question, you know how to do all of them. So we'll go over this again. And this is the only GCD question we'll do. But please make sure you understand this, make sure you know how to do this. Do not waste your precious exam time on this type of question. Okay, anyway, so whenever they ask you to use Euclidean algorithm to find GCD of two numbers, you pick the bigger number. Okay, so we have 95 and 60. 95 is definitely bigger than 60, so we use the bigger number, divide by the smaller number. So we have 95 divided by 60, we'll get 95 equals to 60 times 1 plus 35. Okay? Now, you have 60 and 35. You repeat the same thing. Okay? You use the bigger number divided by the smaller number. So you'll get 60 equals to 35 times 1 plus 25. And again, you use the bigger number, divide by the smaller number. You'll get 35 equals to 25 times 1 plus 10. And you do the same thing again and again and again until you got 0 as a remainder. Alright? This is when you can stop. And your GCD would be your this remainder and your second last row, okay, the non-zero remainder. So in this case, GCD of 95 and 60 would be 5. This is really important because with this we can do the following question. Before we do the next question, let's look at the theorem, Benzo's identity. This identity is quite important, I would say. Once you move on to upper year math courses, you use this all the time. So our a, b are two integers, both non-zero. Then there are integers m and n, such that an plus bn equals to GCD of ab. Please remember this. This is quite important. Probably not in 102, but it's quite important. Because by using this identity, we know that we can find integer solution xy such that 95x plus 60y equals to GCD of 95 and 60. Okay? We know our x and y exist because of this identity. Okay? So how do we solve this question? This is part 2 of the question we just did right here, which means, well, we need to use what we just did in part 1. And I copy-paste part 1 here. Okay, this is part 1. I copy-pasted here. And I labeled each step as 4, 3, 2, 1 because those are the steps we need to use in order to solve this question. So we know that GCD of 95 and 60 is 5 by part 1. We'll start from there, which is your second last step here. I labeled it 1. So we'll start with this. We'll start with your GCD 5 equals to. So you just need to rearrange this equation as right here. 5 equals to 25 minus 10 times 2. So literally just rearranged this equation. Then you can use step 2 here. Okay? You can use your step 2 here. Notice that we always look at the remainder here. Okay? So every time we rearrange the equations here, we look at the remainder here. So now the next remainder is 10, and you can see we have 10 here. So we can substitute our 10 as 35 minus 25 by using step 2. Alright, now we just need to open a bracket and group the like term. And that's how I did it right here. So this step is just group the like terms. After we group the like terms, you'll see that we get stuck. We don't know what to do next. This is the time you check your third step. Okay, so we have 25 here. We have 25 here. We just need to substitute our 25 with 60 minus 35. This is by step 3. Okay, we know that step 3 is here. We know that 25 equals to 60 minus 35. So we do that, and then again you open a bracket and group the like terms. You'll get 3 times 60 minus 5 times 35. Again, we get stuck. You check step 4 right here. Okay, so we have 35 here. We have 35 here. Again, we do the same thing. Substitute your 35 with 95 minus 60. Okay, this is when you use your step 4. And you open a bracket, group the like terms. Eventually, you'll get 8 times 60 minus 5 times 95. Therefore, your GCD, which is 5, equals to 8 times 60 minus 5 times 95, which means your x equals to -5, y equals to 8. This question is quite important. Please make sure you understand this. Most likely they might not give you part 1, so they might not ask you to find the GCD of the two numbers first. So you just start with this question. Okay, so if you see this type of question, you need to use Euclidean algorithm to find the GCD first and do backwards. Okay, so just like this. So you need literally you're just doing backwards of Euclidean algorithm. This is how you find such solution. And the third part of this question is, are there any other integers x, y that solve the above equations? Are there? Of course there are. Why is that? Okay, I'll tell you why is that. If we look at this equation, 95x plus 60y equals to 5. Okay, if we look at this equation, some of you might recognize that this is a line. Okay, a straight line. So the other, probably most of you are familiar with this. Y equals to kx plus b. We know that this is a line. This is the same as this. You can write this equation as something like this. So now we know this is a line. So if you have a line, how do you find your x and y value? I'm sure, because okay, in this case you will know your k and you'll know your b. How do you find your x and y value? I'm pretty sure everyone know how to do that. It's just the x and y value you'll find might not be integers. But think about this line, okay? Think about a line. I'm drawing a line, might not be the one here. But think about this line, how many integer x and y does it have, okay? This would have infinitely many x and y, which means we have infinitely many pairs of x and y to solve this equation. And how do I find the others? This is the time we need to use the technique I mentioned many times. You plus and minus the same number. Okay, this is when we use this. So I wrote the solution here. So we start with this. So we start with your original solution. 5 equals to 8 times 60 minus 5 times, 5 equals to 8 times 60 minus 5 times 95. So we start with this. We want to add a multiple of 60 or 95. It doesn't really matter. Okay? So what I did here is I add a multiple of, let's see, AB. So 60 times 95. And I minus the same thing. Okay? Then you can group them together. This will give you 8 times. Oops, not 8 times. So you group them together. 8 times 60 plus 60 times 95. Okay? Minus 5 times 95 minus 60 times 95. Now you can, group them together as here you have 60 on both sides, you have 95 on both terms. Okay? This is why you have this. Alright? And then if you add those together, you'll get 103 times 60 minus 65 times 95. This is another pair of x and y. As you can see, I only just add a term and subtract the same term, which is like you're adding a 0. That's how we solved this question. But I wrote down the general formula to find, the integer pair of x and y here. So if you have d equals to ax plus by, where your d is GCD of AB, here this will be GCD of AB. Okay, so if you have this, you can just have this equals to x plus k times b, the whole thing times a, plus y minus k times a, the whole thing times b. Okay, this is the same thing as what I did over here. This is the same thing. Okay, if you check, you'll see it's the same thing. What we did here is just we add abk and subtract abk, where your k is just an integer. Okay. The first equation is when k equals to 0. And if you want to find another pair of x and y, you just, let your k equal to 1, 2, minus 1, minus 2, such things, so that eventually you'll get another pair of x and y. This whole thing is also equal to this. The same, as I said before, the same thing, you add and subtract the number. So this case you added ak times a over d, b over d. So this is like ab k over d and minus abk over d. Alright, this is how we got this. But as I mentioned here, this would be integer and this will be integer. Why is that? Because your d is your GCD of AB. Okay, so b divides the GCD of AB and a divides the GCD of AB, which means this is always an integer. This is always an integer, which means the whole thing will be integer as well. So those are the equations you can use, no, not equations, those are the formulas you can use to find another pair of x and y. I do not want you to memorize the equation itself. What I want you to do is understand how we got the equation. Okay, all I did was just add a multiple of AB and subtract a multiple of AB. Okay, just like this, like here. Please, please, please understand this. Do not memorize a formula. I would feel so bad if you memorize a formula. Okay, so understand it. Don't memorize anything. Some other example I did here. Okay, those are just using the Benzo's identity. First of all, prove that if there exist x and y in integers such that ax plus by equal to 0, then the GCD of AB equals to 0. First of all, we make the assumption, literally just copy down this. Then, since we know that the GCD of AB divides A, and the GCD of AB divides B as well, we know that GCD of AB divides the linear combination of AB. Okay, write it down. If you are taking hold on. If you are taking linear algebra, you should know what linear combination is. If not, it's just linear combination of AB is just A times an integer plus or minus B times an integer, which is right here. Okay? So since GCD of AB divides A, GCD of AB divides B, GCD of AB should divide AX plus B, or AX plus BY, which is just 1. Okay, so GCD of AB divides 1. And we know that only 1 divides 1. Therefore, GCD of AB will just be 1. And that's the end of our proof. The second question follows directly from Benzo's identity as well. So by Benzo's identity, we know that GCD of AB equals to AX plus BY for some x and y in integer. And since this is true, D divides A, D divides B. Again, D will divide the linear combination of A and B, which is AX plus BY. And we know that AX plus BY equals to the GCD of AB, therefore D divides GCD of AB. Okay, now Euclid's lemma. This is quite important because we can use this to prove the square root of a prime number is not rational. Okay, so this lemma is talking about that if we have a p that's greater than 0 be a prime number, and a and b are integers, and if p divides the product of AB, then p divides A or p divides B. This is quite important. Please make sure you know this. And please know that your p has to be a prime number. Okay? Now, I'll prove what I mentioned before. The square root of a prime number is not rational. So, as always, naturally you start with contradiction. So, for contradiction, we suppose the square root of the prime number is indeed rational. Then we can write this as A over B right here. If a number is rational, you can write it as this, where your A, B are integers and B is not 0. Also, this is quite important in this question. The GCD of AB has to be 1, because this is later we'll see that we use this to reach our contradiction. So in this question, this is quite important. Okay? Now, since you have this, you can square both sides. You'll get P equals to A squared over B squared, and you times B squared on both sides, you'll get this. This means P divides A squared. Okay? Since P times an integer equals to A squared, we know that P divides A squared. Now you can use Euclid's lemma since, okay, as P divides AB, then P divides A or P divides B. Here our A, B are both A, which means if P divides A squared, implies P divides A. Since P divides A, you can write A as P times another integer. Again, please, whenever you introduce a variable, please define your variable. This is really important. I'm sure I said it many times, but this is really, really important. Now, you can substitute this equation back to here, okay? Which you'll get PB squared equals to P squared times K squared. And then you can divide P on both sides. You'll get this. B squared equals to PK squared. Again, you do exactly the same thing. This means P divides B squared. You use Euclid's lemma, you'll get P divides B. Okay, so now you have P divides B and P divides A. Okay, this contradicts your assumption that GCD of AB is 1. Because, well, if P divides A and P divides B, then the GCD of AB is at least P, which is a contradiction. Okay, so this means your original assumption, square root of a prime, is natural, not natural, is rational, is false. Okay. They can change P to a real prime number. Like they can change this as like square root of 7, square root of 2, square root of 3. Those are all not rational number. Okay, so but all of those questions are using the same logic. Okay, it's literally the same thing. The next very important theorem, the fundamental theorem of arithmetic. You know it's really important because they said fundamental theorem already. Okay, the abbreviation of this is FTA. Fundamental theorem of arithmetic. Every natural number greater than or equal to 2 is either a prime or can be expressed as a product of powers of distinct primes in a unique way. Unique way. Really important. Okay? You can express it as product of powers of distinct primes in a unique way. This expression is unique except the reordering of vectors, of course. This is really, really, really important. As you will see that I'll use this to give you a formal proof of the Cartesian product of countable sets is countable. Okay, I'm pretty sure a lot of you, well, if you watched my last video, I showed you an informal proof of this. I used the zigzag technique. That proof is, I like that proof, but that's quite informal. And here is a formal proof of this. And I used the fundamental theory of arithmetic. First of all, I want to show this, this times this is smaller than or equal to the cardinality of natural number. So I need injective function. So I defined our f from natural times natural to natural, defined by f of ab equals to 2 to the a times 3 to the b. Notice that 2 and 3 here, you can switch them to like 5, 7, any prime number would work, okay? It doesn't have to be 2 and 3. It could be any prime number. Anyway, now I claim that f is injective, so it says like the typical step you prove a function is injective. You let f of ab equals to f of xy, which will give you 2 to the power of a times 3 to the power of b equals to 2 to the power of x times 3 to the power of y. And by fundamental theory of arithmetic, you know the expression has to be unique, which means a has to be equal to x and b has to be equal to y. Okay, so this implies ab equals to xy, which means f is injective and the cardinality of n cross n is smaller than or equal to the cardinality of natural number. The other way is simple enough, so we can just consider a function g mapped from natural to natural times natural, defined by g of x equals to x, or it could be like, x1, just fix one, and then it's the same thing. Okay, this function is obviously injective. Although I proved it here, the proof should be really simple, so I'm not going to go over this. So since g is injective, we know this is true. And then we can use our favorite Schroeder-Bernstein theorem, SB theorem, and we know that this is true. This is the formal proof of this. You can apply this to a lot of other things, such as Q times Q equals to Q, Q times Q equals to natural. The cardinality, they are equal. Yeah, just use the same logic. I don't know if your professor proved this in class or not, but if they proved it, I'm pretty sure you can use this directly. Anyway, I don't know. I didn't go to a lecture, so. The next question is quite important. This is a very typical 102 question. Show that the logarithm of this is not rational. Again, the most natural way, use contradiction. Suppose it is natural number, then you can write it as a over b, where a, b are integers, b is not 0. You can write GCD of AB is 1, or you don't have to. For this proof, you don't have to write it here, but I recommend you to write it here, just in case, well, sometimes you need this condition, sometimes you don't, but there is no harm that you write it down, but you don't need it. Anyway, because we have this, we know this is true, so 48 to the power of a over b is 72. Then we can take the power of b on both sides. We will get 48 to the power of a equals to 72 to the power of b. Then you can write the prime factorization of 48 and 72. Okay, so 48 equals to 2 to the power of 4 times 3. 72 equals to 2 to the power of 3 times 3 to the power of 2. Okay, this you used prime factorization. Please make sure you know how to do this. Factorization. Make sure you know how to do this. So this is this, this is this. Okay, so this implies that 2 to the power of 4a times 3 to the power of a equals to 2 to the power of 3b times 3 to the power of 2b. By fundamental theory of arithmetic, you'll get 4a equal to 3b, a equals to 2b. And you just do manipulation, eventually you should get b equal to 0. This is a contradiction, because your b is a denominator, and here it is, b cannot be 0. Alright, so this is a contradiction, which means your assumption was wrong. This is not a rational number. The last question I'm going to cover is from your tutorial activity as well. Okay? I'm talking about this because I want you to know that, first of all, this equation, the GCD of AB times the LCM of AB equals to the product of those two numbers. I know some of you don't know this number, but this is quite useful, so no harm to memorize it. Actually, I don't want you to memorize it. I want to explain why this is true. But the other thing is I want you to know that there is another way to find the GCD of two numbers, which is you do the prime factorization. Okay, as we mentioned here, prime factorization. If you, okay, so right now your A is 10 factorial, which is 10 times 9 times 8 times till 1. So I wrote it as 2 times 4 times 6 times 8 times 10. And so I wrote the even numbers together and odd numbers together. Oops, this is not this. Okay, so hold on. Just realized I made a mistake here. Why is that? Because your B is 2 to the power of 10. And your GCD is the greatest common divisor. So if you want to find your common divisor, you know that has to be 2 to the power of something, which means you don't care about the odd numbers. Okay? What do I mean by this? This is, I wrote even number here. 2 is 2 to the power of 1. 4 is 2 to the power of 2. 6 is 2 times 3. 8 is 2 to the power of 3. And 10 is 2 times 5. Okay, so now you know this, the GCD has to be 2 to the power of something. You count the number of 2 you have here, so 1, 2, 3, 4, 5, 8. Okay, so you know that 10 factorial is 2 to the power of 8 times a number that we don't care, because we know that's not gonna be the divisor of B. Okay, so the common divisor of A and B would be 2 to the power of 8. Okay, let's recall how we find this. We write down the prime factorization of both of your A and B, and we pick the common ones. Okay, the common ones will be 2 to the power of 8. When you try to find the LCM, least common multiplier, how do you find this? Again, you can write down the prime factorization of both numbers, okay? And then you just get rid of your common ones. You want to remove the repeats. Remove the repeats, what I mean by that. For example, let's see, what number do I want? A equals to 6. B equals to 9. Okay? What is the least common multiplier? How do you find this? Well, A equals to 2 times 3. B equals to 3 to the power of 2. Alright? Now you know that 3 to the power of 2 is 3 times 3. So you want to get rid of the repeats. So this is distinct, this is distinct. Repeat, this is repeats. Okay, so you want to get rid of the repeats. Therefore, your LCM would be 18. Okay, you want to get rid of the repeats. Well, if you look at the GCD of 6 and 9, you know that they both have 3, which is the common divisor. When you look at the LCM, you get rid of the common divisor. Okay, so it's going to be the whole thing divided by the common divisor. What does that mean? This means your LCM of AB equals to A times B divided by your GCD of AB. And this is how we have this equation. Okay, this is quite useful if you want to find the lowest common multiple of two numbers. As long as you have GCD, you know your LCM. Anyway, that is the end of this video. I do think this is the last video I'll post, or at least for this semester. I hope everyone can do well on your exam. And I hope all of you can make it to your post. Good luck in your exam.